All right, so we're going to look at some Pdes exercises. This is a sort of classic solve the wave equation with separation of variables type question. We're given the one-dimensional wave equation here. We're given an initial condition here, and we're given Dirichlet, homogeneous Dirichlet boundary conditions here. This initial condition, we can sketch it out to try and figure out what's going on. X, U, X naught, like so. We've obviously got between 0 and L, L on 2, something's happening there. And then we got L on 2 to L. Looks a bit like a 2. Right, so over this region, we've got some just straight line with intercept 0. The gradient's related to alpha. Or the gradient is alpha. Right, so that's the line there. Here, we've got a negative gradient, and the intercept is obviously down here, right? So it continues on like so, right? So what we've got is we've got a sort of tent thing going on. And this might represent a plucked string. Now, this is one of our initial conditions. I should write down that we've got another. It'll be ut of x comma naught equals nothing. Right, so we do in fact need a second initial condition for this. Let me just check my problem sheet to make sure I've copied it down correctly. I have. So at the initial point, we've got this displacement, which is sort of triangular, like a string that's been pulled upwards to this position, and then it's stationary, right? And that's what this initial condition here says, that this string isn't actually like moving. And we release the initial condition so that the string has to sort of accelerate from rest. All right, this will be separation of variables. So let's crank through that. Let u of x and t be some function x of x, t of t, like this. So we really assume that the functions, the solution we're looking for is multiplicative, is one function of x multiplied by a function of t. So that's the fundamental idea that we then try and separate out. We've got nothing else to do with this other than to plug it into our PDE. So when we plug it into the PDE, we're going to get this, because that's right, that's the only function of time. X is a function of space alone. Then we're going to get c squared. We're going to get t of t, because t is a function of time alone. And now we're going to get the spatial one. Okay. Now we can rearrange this thing. The goal is to get all the t's on one side, all the x's on the other side. Usually also you associate this c, which is kind of a wave speed, you associate that with time, because that's sort of what makes sense. It doesn't actually matter where you put it, it'll all come out in the wash when you finish your solution. So this is what you've got after rearranging to put the x's and the t's together. If you have a function of x on this side and a function of t on this side, and they're always equal irrespective of x and t, the values of little x and little t, the functions must equal a constant, right? So that's the only way that this can magically work out, is if somehow this is constant, and they're both equal to the same thing. So we call this the separation constant. A bit of a trick is to realize that a good choice for the separation constant is minus lambda squared. Minus lambda squared is always negative, right? It's a real constant. So when we square it, no matter what the value of lambda, we're going to get a positive number. So if we stick a minus sign outside of a squared, we're always going to get a negative number. The point here is that this is the only case that gives non-trivial solutions. Now, if you don't realize that to begin with, you might set your separation constant to be equal to just lambda, and then you've got to test three different cases. You've got to test lambda positive, lambda negative, and lambda 0, right? When you go through that testing process, you'll see that the only value of lambda where you get non-trivial solutions for your spatial problem, for example, is lambda negative. So you can either kind of know that a priori, right, and have an expectation, which I do because I've solved heaps of these over the years, or you can set it to whatever and figure it out later. I'm just going to set it to negative because I know that's what works. All right, so now we've got two problems to deal with. May as well write them out. You got one on x, and I'll drop the arguments now for convenience. That's problem 1. Problem 2. Right, and we rearrange. And they're two very similar equations. Right, so you can pretty much treat them as one thing. Now, sometimes you'll often see people separating out the boundary conditions at this point as well. I like to deal with that later for whatever reason. I don't know, maybe that's how I was taught. I can't remember. Let's just go down and write down the solutions of these two problems and then think about the boundary conditions. So the x problem, we're going to get sinusoidal solutions, sine and cosine, right? This is just an ODE at this point, right? So you don't have to worry. If you don't remember how to solve it, you can sub e to the lambda t, get your characteristic equation, or actually some other lambda. You can figure out what your eigenvalues for that ODE happens to be, and work through. But because we're no longer first years, we should be pretty comfortable jumping to this almost straight away. C sine. Okay, so now we've got to worry about boundary and initial conditions. The initial conditions, they just give us stuff about C and D. That's going to come later. We're going to work out lambda and A and B first, based on our boundary conditions. So our boundary conditions are specified for U. So they're specified for all times. They are homogeneous directly, which means that the value of U is fixed at 0 for all time. So let's think about this in an X and T fashion. Clearly, these boundary conditions are what's called separable themselves, and you can actually cancel out the T of T, and you're left with right. So X has to carry the boundary condition information. So now we just want to substitute this into our solution for X. So since X of X is equal to A sine lambda X plus B cos lambda X, we can just plug in directly. X naught equals naught implies sine of 0 is 0. Right, so we've got B cosine of 0 is 1. Right, that's what we're going to get when we plug in that boundary condition. On the other end, now we know B is 0. X of L equals A sine lambda L. Right, and that's got to be equal to 0 as well by the boundary condition. So we've got two choices. Either A is 0, and then our X is identically 0, which is called the trivial solution and is completely uninteresting, or lambda is some multiple of pi. So what we've got, lambda equals n pi over L, where n is an integer. And n can be natural, right? Because you're going to get, it doesn't actually have to be 0, because the 0, if n is 0, then your sign disappears anyway, so you're pretty much done. You're like, that's unimportant. What else do I have to say about this? I guess there's infinitely many of these things. Oh yeah, sign's odd, so you can the contribution of the negative ones can be just folded back into like the positive ones as well. So you don't need to go too hard into that. There's infinitely many of them. They're ordered. There's a minimum one. So this is a Sturm-Liouville problem, and these are the properties of the Sturm-Liouville eigenvalues. Yeah, that's about it. But we are going to distinguish now that lambda is indeed a function of n, and that it also gives us a function of n. It also tells us that A is also indexed by n, because you want to be able to superpose these things. So you have like an elementary x, n pi, like so, and then you have an overall, oops, you can superpose these things like so. All right. That gives us a bit of insight into our T solution, of course, because T involves lambda as well. C is a parameter of our problem. So that's also like, that's something we know, if you like. C and D are going to become indexed by n as well. So we're just going to have to chase down what happens to them. For the moment, let me just check to make sure that I haven't blundered. So far, so good. All right. Okay, so let's look at some initial conditions now. So the time derivative one, that's a nice homogeneous initial condition. So this will actually imply something useful. So when we sub in our product again, we get this equals 0. So you can divide out the x of x, and what you've got in that case is t, little t, like that, oops, of 0. So equals 0. So this, we need the time derivative of our t solution. So if we look at our t solution, we've got sine and cosine. So we've got to differentiate that. So that's equal to c. C differential of cos is minus sine. So that's the big and little. I'm going to pick up a lambda as well. When I differentiate sine, I get cosine, and it's positive, so I just pick up that. Okay, so now t, little t, 0. Sine is 0 there, so this is the bit that's got to go. Equals 0 implies d is equal to 0. So what actually survives is c, which started off life as our oops. Sorry, I got them around the wrong way. Everything I said was still true. I just wrote my solution with C and D swapped, right? I made that mistake. So hopefully just quickly fixing that didn't confuse any of the matter. The cosine's got to disappear because sine of t, when t 0, it's already gone. So the what survives is our d, which was originally associated with our cosine. So t of t so far is equal to d cos lambda t. Now lambda is a function of n, so we're obviously going to get to superpose this as well. But we should also be looking to substitute in what values we had for lambda. So that's d. The wave speed's still kicking around in there, and that's just substituting the value of lambda that we found before. So now we can put this back together. So our u xt equals x of x, t of t equals d, which is some constant, an, which was the constant I think we had, that was the one that survived from up here, sine cos c n pi t on L, like that. This is from n equals 1 to infinity. And this DAN thing, right, that's just some other constant. And to make that consistent with the solutions written in the notes, I'm going to write little an. All right. Okay, so far so good. What we have to do now is we have to use our final boundary initial condition, This is the unseparable IC. That was U x 0 equals like that step function thing. We'll just write f of x and recall that it looks like this, right? That changed at L on 2. That's unseparable because it's got this function x and still tangled up in time. So let's now apply that to this problem here. So we can go U x naught, plug in naught here. That's equal to the sum from n to infinity, little a n. This cosine term just becomes 1 because t is 0. So we're left with sine n pi x over L equals f of x. Now, that's great. It's not very helpful because we want to find these ANs. We're going to use the orthogonality relations. Now, you can either look these up or you can prove them. They're not too hard to prove. They all come out of trig identities. The important one that we need here is the integral from 0 to L of this function times this function with respect to x is equal to what is it? L on 2 when m is equal to n and 0 otherwise. Right, this orthogonality relation lets us get rid of this summation, right? So what we do to apply this result is we multiply through by this thing, then we integrate, right? So we've got to multiply both sides by sine m, integrate. We assume, well, we know that swapping the order of summation and integration works if your functions are analytic and sine's analytic. So what we've got is this. Dx, there's our integral, equals integral 0 to L f of x sine m pi x on L dx. All right, so everything where m is not equal to n, you're going to get 0, right? The only non-zero term now in this thing, and if you like, you can swap that. As I said, the only non-zero term here is going to be when m is equal to n. So on the left-hand side, we're going to get L on 2 times an, right? Because this is the bit that changes. This is m equal to n equals this bit where m is equal to n as well. Okay, so often what you'll just see is you'll see this as the quoted result. So you'll often see like this in a big box somewhere. Fourier sine series coefficients are this. Well, that's using the orthogonality relationship to apply it or to find them. Now, we actually know f of x in this case. F of x is actually quite a nice function. Even though it's piecewise, you can actually evaluate this integral explicitly. So not always can you do this. Right, so we're kind of fortunate in this case to be able to do it. So let's give it a crack. So we remember that f of x equals, it's 2 on scroll, 2 alpha x over L. And then the other one is 2 alpha 1 minus x on L. That's x less than L on 2, but greater than 0. The actual equality doesn't matter. L on 2, x, L. You know that it's not equal at the boundary conditions, though. All right. So essentially, we plug this in. We're going to get 2 contributions to the integral. One up to L on 2, and then one from L on 2 to L. So AN equals 2 on L into 0 to L on 2, this bit, 2 alpha Lx sine n pi x on L dx. Right, so this will be an integration by parts, because essentially you're integrating x sine x, right? That's really kind of what you've got here, with a couple of constants floating around. You can, of course, check a standardized table. This is one of the integrals that will be tabulated. The next integral has got 2 parts in it, so I'm going to break those 2 parts out as well. Still got the 2 on L out the front here. And we're going to get a 2 alpha out the front of both of these. So 2 alpha integral L over 2 to L of 1 times sine n pi on Lx dx. Then the next bit is got a 2 on alpha, it's got a minus, and it's actually got an L as well, so minus 2 alpha on L integral L on 2 to L x sine n pi Now, there's very few other results that I can see to assist with this integral, so I just probably got to do them. This bit and this bit will end up canceling. Most of this will end up canceling out, actually. This bit's the most tractable part of the integral. That obviously just gives you a cosine, so let's do that one first. Gives you 2 alpha L on n pi. Integral of sine is minus cosine. N pi Lx between L over 2 to L. So that's minus 2 alpha L n pi. So when we sub in L, we're going to get cos of n times pi, which is 1. Or when we sub in L on 2, we're going to get n pi on 2, which for cosine is 0. All right, so the yellow part of this integral gives us 2 alpha L on n pi like that. All right, so let's do the red integral. Now, this, like if we do the indefinite integral, because this one here, it's obviously the same integral, just with different limits. right? So if we just do this indefinite integral, we've really done this one as well. So yeah, that's not 0 or 1. That's a mistake. That's either plus or minus 1. So let's just keep this as cosine in pi, like that. Bottom one's still 0 because cos of n pi on 2 is 0. All right, so let's take a crack at integral of we're just going to park a 2 alpha on L out the front. X sine n pi on L x dx. Right, so this is by parts. The one you differentiate is x. The one that you start with, assuming it's the derivative, is the sine. So v is the integral, so that's minus L, like that, of cosine. All right, so now we stick this in. uv minus the integral of v du. So du is just dx minus, so that's going to become a plus L on n pi cosine. All right, integrate this one. Like so. So this, even though I'm doing the indefinite integral, I've got a plus c here. I'm just going to take that as 0 because I know that I'm going to be subbing in limits to this. Right. For my first integral, I'm going to plug in the limits 0 and L on 2. Okay, so minus L on n pi. What happens when I plug that in? I'm going to get cosine of cosine. Oh, 0. Oops. I shouldn't just randomly cross that out, should I? Oh, and I should carry on my 2 alpha L. Okay, so L, plug in L on 2, I'm going to get an L squared there. When I plug in cosine, I'm going to get n pi on L on 2. Right, so that's always going to be 0 no matter what. Plus L squared on plug in L on 2, I get sine n pi on 2, which is non-zero, minus I've got to plug in 0 to this, so obviously that's just going to be 0. This has got a sine term in it, so that's also 0. Right, so once I'm finished, that's 0. So I'm left with this bit, 2 alpha on L squared on n squared pi, like so, sine n pi on 2. Okay, so that's the red integral here. All right. I was rather hoping this term would cancel or go away. I'll have to go back and check that that calculation's correct. Let's just proceed and do the black colored integral for now. So we got now a minus minus 2 alpha out the front, 2 alpha on L times all of this, right? So I've just got to carefully copy. Minus Lx on n pi cosine n pi x on L plus L squared n squared pi squared sine n. Right, so as I explained, I was cheating. I'm just going to do. I've got the indefinite integral, right? So I can just plug in different limits. So now I'm going from L on 2 to L. So let's stick that in. When I plug in L over 2 in here, oh, so I want to plug in L, right? My top limit is L. So plug in L squared on n pi, like that. Then I'm going to get cosine n pi. All right, excellent. When I plug in my top limit L into here, I'm going to get 0 because I'm going to get sine of n pi. All right, so now my bottom limit. My bottom limit's L on 2. When I plug in L on 2 here, I'm going to get something, but I'm going to get cosine of n pi on 2. So I'll just write that out. Now it's minus minus, so that becomes a plus. So this is 0. And when I plug in L over 2 into this thing, right, which is not 0. Now, however, that's a minus, right, because this is my bottom limit. So I've got to keep track of that sign. Okay. Alrighty, so once I've got this, I can write it all out, equals 2 alpha L on n pi cosine n pi minus, so minus minus plus 2 alpha L n squared pi squared sine n pi on 2. All right, so I've got the contribution from the yellow one, which is cancelled by this term here, right? So notice that when I add all of these things up, because I incorporated my sign here, remember, See, it's that sign there is that sign there. So this one in fact cancels here. Excellent. I knew I had to get rid of that. This one has a contribution that looks like this that adds to this. So overall, I am left with, when I sum this, so take this one, take this one, and take this one, and I add them all up. And of course, multiply by the 2 on L out the front there. I'm going to get 2 on L into, oh no, wait, sorry, the red one is the first one in sequence, so 2 alpha on L squared, I'll just knock that out, n squared pi squared L sine pi n on 2. Then my yellow integral's the next bit, minus 2 alpha L n pi cosine n pi. And now finally the black one, plus 2 alpha L n pi cos n pi plus 2 alpha L n squared pi squared sine n pi on 2. All right. So when it's all said and done, good night. This is just that, right? So this whole thing is equal to, when you add them up, you get 4 on the inside, you multiply by another 2, you get 8 alpha. Oops, that's an alpha. When you divide through by L, that L goes, so you got it like this, sine n pi on 2. All right, and you can actually figure out what this has got to be. This is pi on 2. This is 3 pi on 2, and so on and so forth. So you could actually, this is plus 1, this is minus 1. You can actually write that as a power. So in this case, n is equal to 1, n equals 3. Right, so you could write that, you can write that as a power of minus 1, but that's kind of tedious, and we'll just leave it at that. So that's actually what our an is equal to. And we're done. And that's the answer I got on the cheat sheet as well, so go me.